This session is Brant Robertson. So he will talk about Morpheus, a deep learning framework for a pixel-level analysis of astronomical data. So please.
All right, thanks so much. Thanks for coming back from the break. My name's Brant Robertson. I'm here at UC Santa Cruz, and today I'm going to tell you about some of the thesis work of Ryan Housen, who is here at UC Santa Cruz in the Comp Sci department. He's been working with me on what we're calling Morpheus, which is a deep learning framework for analyzing astronomical images. Now, you may be wondering, Brant, why aren't you talking about simulations? And we have plenty of simulations to talk about. You may know that I've done a lot of work on GPU computing, GPU-based simulations. Another thing that GPUs are very good for is deep learning. And so I thought, well, why don't I dip my toes in this a little bit? And then I became more and more excited about it, especially working with someone as capable as Ryan. His paper is now out on the archive, and of course you can go to his GitHub site. You can download the code. You can try to use it yourself. There are tutorials. I'll tell you more about that in a little bit. So what's the motivation, the scientific motivation for something like Morpheus? Well, you know, this seems like a cliche to say, but we really are so close to a revolution in the data that we'll be receiving in astronomy from missions like JWST, like LSST, and like WFIRST. So I'm on the steering committee for the JADE survey, which is the GTO survey with JWST. We'll be taking the first large area deep survey with JWST in Goods North and Goods South during the first year of operations with JWST. This will be a fantastic data set. You know, the new candles, the new goods with JWST. I was also for several years the Galaxy Science Collaboration Chair for LSST, so I'm very interested in large area surveys and big data. And so how do you analyze that data? And then the Wide Field Infrared Survey Telescope, WFIRST. I'm on the Formulation Science Working Group for WFIRST. This is kind of blending the two approaches together, doing large area surveys in space with high resolution and lots of pixels. So, you know, we want to be able to interpret and understand this data and process it in a way that is informative as quickly as possible, and also to try to, you know, eke out every little bit of information that we can get. Of course, eking that information out is quite complicated because, as we all know, astronomical data are richly complex. So you look at this image, which is, you know, somewhere on the sky. I don't know. It's an HST image. I forget now. But it's a multi-band HST image of one of the deep fields. And you can see, you know, there's a lot of variation in the structure of individual galaxies. There are stars. We all rely on this information to tell us about the history of the galaxies, to tell us about their formation, to tell us about what's going to happen to them in the future. How we connect them together is largely interpreted through these data that we receive, these multi-band images. Okay, so let's talk about the way in which we go about learning from these kinds of images. And there are really kind of two main steps in that process. The first step is the where. We look at these complicated images and we think of, where are the objects in this image? How do I decide which pixels in an image are of interest? Okay, and one standard way of doing this is to use some kind of extraction software. This is S-Extractor here. And you can see that based on the peaks in this flux distribution, I can identify pixels that are some, say, RMS flux, or some flux above an RMS background. I can identify the pixels that I think belong to that image, the contiguous pixels above some flux limit. I can measure some properties and, say, draw some ellipses based on what the principal component axes of these flux distributions are. This is very standard. I think almost everyone in the room has used a data set that has been characterized in this way. But once we have that information, once we know where the objects are, you want to ask kind of a higher level question, or a deeper question in some ways, and that is, what are you looking at? How do I describe what is here? And so this is a figure from Jehan Karteltepe's work, where she led some people in the room actually in a really you know, well-engineered approach of looking at the individual galaxies with multiple different humans, expert astronomers, classifying images and trying to say, well, I think this is a disk, this is a spheroid. People voted. They recorded the uncertainty in the votes in the sense that multiple people might say it's a spheroid, multiple people might say it's a disk. All of that information, the actual intrinsic kind of systematic uncertainty in the visual classifications by humans was recorded, and so this is really proven to be a great data set for understanding morphological classifications of galaxies. And people have then since trained machine models, and I'll tell you about machine learning models in a little bit, to go about reproducing that kind of classification. So a lot of this work actually was pioneered by Mark, who is talking next, I think, and then Helena, do you want to raise your hand so people know where you are? Helena Dominguez-Sanchez, another pioneer in this as well. And so we've really benefited from the insight that they've brought to the table in learning how to use deep learning models to actually reproduce this kind of visual classification that humans have done. Of course, you may know about Galaxy Zoo as well, where people have been enrolled on the internet to look at pictures of galaxies and trained to classify them. And Mike Walmsley, who is probably still in ISB, he's here on campus, is one of the people using deep learning to improve and extend the Galaxy Zoo classification. So this is definitely interesting work that people have been conducting. We're going to kind of blend these two methods together. So our idea, which Ryan, I think, was the first to implement that I'm aware of, was to do both source segmentation and classification at the same time. So how would you do this? Well, if you're interested in making billions of dollars, or at least spending billions of dollars on autonomous vehicles and engineering them, you have to train autonomous vehicles to actually navigate very complicated environments. And the way they do that is by gaining some kind of sensor data, let's say a picture for our intents purposes here. They have to go into that picture, they have to identify things of interest in that picture, say a sign, a pedestrian. So they actually do source identification in their images, and then they have to do some kind of classification as well. They have to train their models to classify that this thing is a sign, this is a person, don't hit that, that's a pedestrian, okay? So we can actually use the techniques that they engineered on astronomical data sets. And this was Ryan's insight. So what he decided to do, and this is a kind of a summary, and then I'll go into the details, was to develop a model which we're calling Morpheus, which is pixel-level semantic segmentation of these astronomical data sets. So here's a VJH multicolor image. The model goes through and it tells you which of the pixels contain flux of interest. Okay, so it does source identification by separating out background pixels with pixels that contain objects. And then for those objects of interest, it tells you some kind of morphological classification. So here we have a disk, we have a point source. You can see that where the flux is low, the model becomes a little bit less certain about what's there. But we can get around this by doing flux-weighted classifications of objects, and I'll tell you more about this in a moment. So for those who aren't fully aware of what a convolutional neural network is, I'm going to give you a brief overview slide, and then I'm going to show you some of the guts of Morpheus. I'm going to go through that very quickly because the details for the experts you can ask us separately. For those who don't care about it, just bear with me for a moment. So what is a convolutional neural network? Well, it takes an image as an input, so here's an image of a galaxy, and it convolves that image with kernels. These are convolutional kernels. The parameters, the shapes of those kernels, are actually parameters of the model. So the shapes of these convolutional kernels are things the model learns. So for each one of these convolutions, you produce what's called a feature map, which is a convolved image, a convolved version of the input image. And you can collect those feature maps together. You can flatten them, so they're matrices, they're images. You just take out each row and kind of stitch them together row by row into a long list of numbers, and then you can feed that into a neural network, and you train the parameters of the neural network in training, and then you can output some kind of classification. So the output from this would be, say, 30% disk, 20% spheroid or something. Okay. So that is the general overview of a convolutional neural network. However, sophisticated models are a little bit more complicated than this. So let me just give you a brief overview of the way that Morpheus does it, and then I'll continue on to the results. We use as input multi-band imagery. Okay, so we're not using PNGs, we're not using JPEGs. A lot of the models that have been trained to classify images on the internet, that's the input that they use. Instead, we use science quality fits images as our input, and we're using V, C, J, and H for the time being, although the model can use others and be trained differently. Once the data is input into the model, it is operated on by a successive set of convolutions. So there are many, many different types of convolutions that the model goes through. And at each step, there are different numbers of convolutions that are performed. Okay. So the details of this become somewhat complicated, and the shape and the structure of the images change as they flow through the model. The details of this are not terribly important for the purposes of this talk. Many of the structures of these kind of models are learned heuristically. You try out different things and see what works. The detailed theoretical models, the mathematical models behind this are pretty complicated and difficult to explain in detail. In fact, they don't work very well for very complicated models. But what people do is they forge ahead, they try different things, and they see what works. And what works means basically you compare against some kind of training set and you see how well you can reproduce what you know the answer is. This is something that we're pretty familiar with in astronomy. We often don't know how we get the answer. We just sometimes forge ahead and do things heuristically. And so this is early days still with machine learning. And so some of the structure of this model could change in the future. I don't know. Okay, so as the data descend, there are a variety of operations. Like I said, there are convolutional neural networks that are basically stacked end to end. We also do something called max pooling. This basically takes of a 4x4 subset of the image, the maximum value of those pixels, and then makes that into a smaller and smaller image. So there's a contraction phase where the image data is getting smaller, but there are more separate individual images produced by different convolutions. And then there's an expansion phase where basically you use bicubic interpolation to stretch the image out again from this resampled data here. And then eventually there's a final set of convolutions that produce 5 different images. Okay, those images have the same format as the input images, but they mean something different. Those 5 images tell you what the model assigns as, we'll call it a probability, but it's difficult to think about it exactly in those terms. The probability that a pixel is, say, a background pixel, a spheroidal galaxy pixel, a spiral, an irregular galaxy pixel, or a point source / compact pixel. Okay, so if all of that was a bit quick, I understand, and the reason is that the details of these models are not familiar to the community yet. You can look at the paper. We did our best to try to describe what happens in detail, but let me show you what the results are, and so then we can discuss the detailed results of the model. They'll be intuitive to you, I hope. So here's a space telescope V-band image, okay, just a part of Candles in Good South. Here's the Z-band image. I'm just showing these so that people get some familiarity with the different, these are the same stretch of the data, so you can see the structure in the image change. And then we'll go to J-band now, which, the structure of the noise changes, the smoothness of the image increases because the resolution is poorer. All right, so this is a RGB image, so this is just creating a multicolor image from those 3 data sets. Then what we do is we feed this multicolor image, the set of bands, the individual fits images, into Morpheus. And what Morpheus does is it scans through this image, and it feeds a subset of the image into that model repeatedly. Okay. As that subset of the image is fed into the model, for each pixel in that subset of the image, it decides whether that pixel is spheroidal, disk, a background pixel, irregular, point source, compact. And then as we scan through, we have multiple different classifications for every pixel. So we have some scheme for determining what we think the best class of these classifications is based on that distribution of classifications we've done previously. And this allows us to go ahead and decide what we think the most accurate classification for the pixels in that image are. Okay, so in this image, you can see that green corresponds to irregular galaxies, blue corresponds to disk galaxies, red are spheroidal galaxies, yellow are compact point sources. As this proceeds, you can see that the model is updating the information that it has. It figures out, well, based on this new reclassification where I've shifted the image and reclassified it several times, many times, almost 1,000 times, I think, now I think a spheroidal model is a better classification rather than a disk, and it'll update the pixel and proceed from there. Okay. So I'm going to let this run just a little bit more. We probably don't have enough time for it to go through the whole thing. So, so let me show you kind of what the results of this are for a large image like this. So this, again, is the RGB image. This is the background pixel classification. So here it's a negative image. So large background is in black. Small background probability is in white. You can see that it does source detection. This is the disk galaxy classification. So here, intense blue, the model thinks it's very likely part of a disk galaxy. Red, spheroidal. Green, irregular. Yellow, compact point source. Okay. Then what we can do is, among those different classifications, we can make an image where the color of the pixels indicates what the top classification, the most likely classification according to the model is. So here you can see that disk galaxy, if I advance ahead, is thought to be blue, this one here as well. You can see here this bright object in yellow. Well, that's a star, that makes sense. And you can go through object by object as you wish through the image and kind of do this comparison. We do this in detail and actually train the model, like I said, on Jehan-Kartal-Tepe's data, but then we can go back and evaluate how well the model works by comparing with their data as well. We can also go to known astronomical objects, say 3D HST objects, and we can use the pixel classifications from our model to determine how to segment up the sky based on which pixels the model thinks are not background. Okay, and this allows us to separate out, based on 3D HST objects, different regions that then we can do flux-weighted classifications are and come up with an object averaged classification to compare against Jehan's data. So that's the way we do that comparison. And the model works on a huge data set. So here we've fed it all of the Hubble legacy fields data reduction for good south. And so now we have 100 million pixel classification of all of the pixels in the good south data set. And actually Ryan released all of these different classification images, the ones that tell you the probability for each pixel, whether it's background, irregular spheroid disk, point source compact, and then we have this kind of multicolored classification image for you to compare with. So if you're interested in that data for your own work, please just go ahead and download it and talk to us. So let me give you, just in the last few minutes here, some evaluations of how well the model works. So we can say, how complete is Morpheus relative to 3D HST? We trained based on Jehan-Kartal-Tepe's data set, and you can see where Jehan is complete, we're extremely complete. We detect objects with less completeness down to very faint magnitudes, but we actually do detect objects at 29 AB magnitude, even though the model was only trained to a flux limit of 24.5 AB magnitude. So it's doing even better than you might expect, given the data set that it was trained on. We can also feed the model example images, say a Cercic profile, so a simulated image of a Cercic profile. And we can classify those Cercic profiles as a function of the Cercic n and the effective radius. And the model does surprisingly well on classifying those within the context of the way that we usually think about Cercic profiles. So Cercic n or lower tend to be classified as disks. Cercic 2 to 4 tend to be classified as spheroids. And higher Cercic n profiles or very, very small RE profiles tend to be classified as compact or point source objects. One of the interesting things you can do is automated morphological decomposition. So if you have a large galaxy that has a complicated morphological structure, like this disk has a bulge, often Morpheus will tell you, hey, there's a bulge there. There's a spheroidal subset of that galaxy. I'm not sure what's happened here. Okay, so this is a way of doing an automated morphological decomposition. It doesn't work for all galaxies, but it works for large ones. You can also do morphological deblending. So here we have a star galaxy blend, and the per pixel classification that Morpheus gives you tells you, hey, these pixels are associated with a star. These pixels are associated with a galaxy. You might think about separating those out in your segmentation and realize that they are different things, even though they overlap spatially, the flux distributions overlap. Okay, so the deep learning model gives you a way of doing this kind of deep blending. The whole code is available. One of the great things that Ryan has done, he wants people to try to use it. So he's He's released tutorials that you can actually run yourself on Google Colab. So you can go, he walks you through classifying an image, making a segmentation map, and then colorizing the image so you can see what's in it. So you can use this with your own data. He's also made a website, which I'll scan through here, where you can actually interactively look at the data and look at the different classifications pixel by pixel. So this is the Hubble Legacy Fields reduction of Good South that you're seeing. This is a multicolor image of that. And you'll see in a moment, you'll go up and you can select out any of the different bands you want to look at individually. So I'll scan through several of those. This will just take a second. And then you can go right away and see what the Morpheus color segmentation, or the different, here's a spheroid, disk, irregular, point source, backgrounds, and then the Morpheus color classification, hopefully, yes. So you can see this is a disk, those are point sources. So have a look for yourself if you're interested in that. Okay, so I just wanted to introduce the model to you. The data, the first kind of methods paper is on the archive now. You know, there's the idea that we can apply this to many other different types of data set other than morphological classification. So we used and trained against Jehan Cardell-Tepe's data set. But if you have other data sets like photometric redshift, spectroscopic redshift, other properties of the galaxies that you think that the photometry alone can tell you about, we can retrain in principle Morpheus to give you some handle on those properties for large data sets. The data is available. You can download the model. You can also pip install the model. This is pretty amazing. You can just pip install Morpheus, basically, and then use it for yourself with Python. There's also Docker images for you to try out Morpheus yourself. And if you have any questions at all, again, the whole code data set is online, and Ryan and I are happy to talk to you about it. All right, thanks a lot. Thank you.
Questions?
Lots of questions.
So yeah, at UMKC, we've been thinking about doing a similar thing with machine learning, and one of the things that we've been concerned about is overtraining our pipeline. And I was wondering if you had maybe tried applying this data to a non-candles data set. Like, since you use candles to train it, like maybe Sloan galaxies or something like that. I know the high redshift universe doesn't look the same as like low redshift, but the objects are very similar. So I was wondering if just any other galaxy data set, if you recover the same results.
Yeah, so let me be a little bit clear about what we actually trained on. So we trained on a subset of the candles data, just individual thumbnails, and then we went and we actually classified all of Good South, which includes many other galaxies that aren't visually classified already. Now, it's difficult for us to evaluate the morphologies of those. We don't know them. We're trying to learn them. But we have done specific comparisons where we've gone through and by eye did some sanity check there. So that's not a statistical proof by any means. But you know, what we plan to do is apply this to the other candles fields where we have these bands. We think in order to apply the model to other data sets, you might have to retrain on other bands if they're not using the same bands. We're gonna try that. It's still early days for us, but yeah, we're on our way with that. Yeah.
As you separate disks and spheroids, can you tell us about the role of dust in Morpheus?
Yeah, so that's a good question. So we haven't looked for like dust lanes or anything like that. We have looked at what the bulk colors are and whether there are trends in the classifications with color. However, we haven't looked for trends in the classifications controlling for the morphology. So for instance, if we had a dustier disk galaxy, would it be classified as spheroid if it had more dust or something? You know, those are things that we're still looking at. We have done a variety of tests where we've injected fake sources, tried to recover them. We've done the kinds of tests that many methods where you're actually doing source extraction and photometry would want to do, just like you were doing it in a standard way. We have done many of those tests, but we haven't looked at dust specifically in that way. Yeah, sorry. Yeah.
Over here.
I don't see.
Right here.
Okay, hi, Michael.
So you mentioned deblending with like stellar sources or you know foreground sources. Can you also do like a separation of merging galaxies? So can you actually identify two separate galaxies that are actively merging and robustly pull them out? And or even like let's say galaxies with with two cores of
Yeah.
stars and stuff
so
like that.
that initial video that I showed you was a pretty complicated blend. And as you saw, it did a good job in separating out all of those different components. And by eye, I think most people would agree that it did the classification of those blended objects correctly, the individual components. So, the way that Ryan does his model, it does a kind of a hierarchical deblending of those sources. So we can go and look when we have sources that are overlapping, whether the model in terms of comparing against visual classifications does a good or bad job. We haven't done that specifically for blends, but that's something that we could definitely look at.
Okay, thank you, Brant. So let's thank Brian again.